In this lesson, we're going to learn about acid-base titrations. So a titration is a method that we use in the lab to determine the concentration of an unknown acid or a base. So the acid or base that we don't know the concentration of is called the analyte. So we're going to analyze that to determine its concentration. And the way that we are going to do that is we are going to use a certain volume of that unknown analyte, and we are going to use a solution that we know the concentration of. So that is called either the standard solution or the titrant. So we will use the opposite. So if my unknown is an acid, then I will use a base that I know the concentration of, and I'm going to figure out what volume of that I need to neutralize the analyte. So those of you who were in class when I did this have already seen what that looks like. We talked about it with the other cohort, and at the end of this slide deck, there are 2 links to videos that show you what a titration looks like to help it make more sense. So the end point of a titration is the point where an indicator is going to change color. So remember, we talked about different indicators that we can use to determine the pH of a particular acid or a base. So we are going to add an indicator. Remember, they change colors within a certain range of pH. So for a titration, depending on what type of acid and base we have and which one of those 2 is our analyte and which one's the titrant, we will use an appropriate indicator for that to help us determine the end point. The equivalence point is the point where our concentration, or not concentration, but our number of moles of the hydrogen ion that comes from the acid is equal to the number of moles of hydroxide ions that comes from the base. So the end point is a little bit past the equivalence point, but that is the point that we can see in the lab. And there's such a small difference in the volume from the equivalence point to the end point that we will use the volume that we can actually see with the end point to help us do the calculations. So there is a very abrupt change in pH at the equivalence point, and so this is where the small change in volume will make a big difference in pH. So for example, if I start with an acid, it's going to go along like that for the pH, and then there's going to be a big jump, and then it's going to level off again eventually. And so the equivalence point is going to be over here. The end point is up here, and you can see that there's not a huge difference in the volume added at that point. And so because of that, this is what we can actually see in a lab setting, and so that is what we are going to use for calculations. So the indicator chosen, as I mentioned, is going to be based on the range of pH where our equivalent point is going to be. So we'll use an appropriate indicator there. The solution of the endpoint can be basic if we have a strong base and a weak acid reacting. So our endpoint there is still going to be a base. If we have a strong acid and a strong base, there we're going to make only salt and water, and the salt is going to result in a neutral solution, and we'll learn the details of that in the 4U course. And if we have a strong acid and a weak base, then our endpoint solution is going to be acidic. So once again, we'll learn the whys of that in 4U. So this is what the setup looks like. So those of you who were in person saw the burette, and this is where we put our known concentration. So our titrant comes in here, and through the lab we will measure the volume of the titrant that gets used to titrate the analyte. So this is a specific volume that we choose, and we don't know the concentration of this. So this one is using phenolphthalein, so that's clear when it's not in the right pH range, which I think is about 8.4 to 10, and then it turns a very light pink when it's around 8.4, and then a much darker pink. So this would be where we're trying to end here. So this would be the end point. The equivalence point happens right before that, but the volume difference is so small between those two because the graph is so steep at that point that we can use the end point to calculate what would be happening at the equivalence point. So this, once again, is the analyte. That is our unknown concentration. So it could be an acid or a base. And then our titrant goes in the burette, and that is our known concentration. And through the lab, we will measure what volume of this is needed in order to get to this point with the analyte. So color-wise with the indicator in there. So we're looking at acid-base neutralization reactions. And we are going to use the stoichiometry from a balanced equation, as well as our concentration equals number of moles divided by volume in liters. So neutralization reaction is acid and a base combine to create water and salt. And so an example here is hydrochloric acid combines with sodium hydroxide to produce water and sodium chloride. So in this situation, I have a strong acid and a strong base, and whoops. No, stop. And yeah, so we had talked about in our last lesson strong acids and strong bases, and I need them in a 1-to-1 ratio here. So remember, this neutralization reactions are one of our examples of double displacement reactions. Okay, so titration reactions, we're going to start with a balanced equation because we need mole-to-mole ratios of acid and base. Whatever our titrant is, so this is the thing that we know the concentration of, at the end of the lab we will know the volume, and so I'm going to calculate the number of moles of that I have between the concentration and the volume used. In the lab, we are going to run at least 3 trials. And for those of you who were in class, we also talked about we do 1 trial quickly and we don't use the results from that just to find the approximate volume, because in the end we are going to be adding drop by drop. So very small volumes at a time, but we don't want to, if it takes 20 mils or 30 mils to complete the titration, we don't want to do that entire 20 or 30 mils drop by drop. So 1 trial is done, and that means we'll end up with maybe that darker pink color, and that gives us an idea of the approximate volume. And then after that, we will do at least 3 trials, and those are the 3 that we would use to calculate the average. We will then use the mole-to-mole ratio from the balanced equation to figure out, given the number of moles of titrant we have, how many moles of the analyte would there be at that point, at that end point. And then once we have that number of moles from the mole-to-mole ratio, we know the volume, and so we can then calculate that unknown concentration. So let's go through an example so that makes a bit more sense. So I have here hydrochloric acid of an unknown concentration. So that's my analyte, so I know my volume for hydrochloric acid. So hydrochloric acid volume equals 25 mils. I'm going to divide that by 1,000 to get to liters, so 0.025 liters, because concentration is in molar, which is moles per liter. So that is going to be titrated with the titrant or the standard sodium hydroxide solution. So sodium hydroxide uses 14.84 milliliters. Oops, and I'm going to divide that by 1,000, so 0.01484 liters. and the concentration of that is 0.675 moles per liter or molar. So I want to find the concentration of hydrochloric acid. To do that, concentration equals number of moles divided by volume. I don't know my number of moles, so I need to solve for that. Before I can get my number of moles of hydrochloric acid, I need to figure out my number of moles of sodium hydroxide. So that's concentration times volume. So I have 0.675 times 0.01484. So my number of moles of sodium hydroxide is 0.010017 moles. And we did just see the balanced equation for this reaction. So hydrochloric acid plus sodium hydroxide gives sodium chloride and water, and this is a balanced equation. So it's a 1-to-1 ratio. So if I need 1 mole of sodium hydroxide, or if I use that much, I will need 1 mole of hydrochloric acid. So here, what this means is 1-to-1 ratio. So if I have 0.010017 moles of sodium hydroxide, that is also my number of moles of hydrochloric acid. So to go from my number of moles of sodium hydroxide to hydrochloric acid, it's the exact same. So just multiplied by 1. So here now I can calculate my concentration for hydrochloric acid. So I have 0.010017 moles of hydrochloric acid, and I used 0.25 liters. And so that is going to equal 0.40 moles per liter or molar. Okay, we'll do another example. So this one gives us our 3 trials. So on the burette, you will read the initial reading. So we're starting not at 0, but at 0.10 for the volume. And then the final volume reads 12.42. Because I didn't start at 0, that is not my final volume. So I have to do a subtraction there. So the actual volume I used in the first trial was 12.42. So then you can see our starting point on the burette for the second trial is the same as where we ended for the first. So I finished my trial here. I got a new flask with a new sample of analyte, which was 10 mils of sulfuric acid. But my starting point for sodium hydroxide was still the 12.52, and then ended with 24.98. Difference here means the total volume of sodium hydroxide used in that trial was 46. So those are my 3 volumes here. So this calculation you have to do after you finish the lab. These are your results that you record during the lab. Then subtraction will give you your actual volumes. So here, to calculate my average volume for sodium hydroxide, I'm going to add those 3 volumes from each trial and divide by, I have 3 trials. And so my average volume here is 12.47 milliliters, or 0.01247 liters. So I have my titrant is sodium hydroxide. So I'm going to start with that. So I have a concentration of 0.100 mole per liter, and I just calculated the average volume of the 3 trials to be 0.01247 liters. So from that, I can calculate my number of moles. It's equal to concentration times volume. Which is equal to that many moles. So for hydrochloric acid, what I do know is my volume there was 10 mils, or 0.010 liters. This is the amount of sodium hydroxide, but if I have, and not hydrochloric acid, but sulfuric acid. So H2SO4. So my balanced equation then so I have sodium is going to pair with sulfate and hydrogen pairs with hydroxide. So I have two hydrogens. One hydrogen will pair with a hydroxide to make water. And that means I have a second hydrogen, so I'm going to need a second hydroxide. So that's going to produce two waters there then. And sodium hydroxide, sodium is a 1+, sulfate is a 2-. So when we crisscross, that gives us Na2SO4. So that is now balanced. So what this means is for every 2 sodium hydroxide, I need 1 sulfuric acid. So 2 moles of sodium hydroxide require 1 mole of sulfuric acid. So to go from sodium hydroxide to sulfuric acid, to go from 2 to 1, I'm going to divide by 2. So that means I need to divide my number of moles here by 2 to get to my number of moles of sulfuric acid. So I have 0.001247 divided by 2 is equal to 0.006235 moles of sulfuric acid. So my concentration equals number of moles divided by volume, which is 0.006235 moles per 0.010 liters. So that is going to give me 0.06235, so 24 mole per liter or molar for my concentration. And then, as I said, we have a couple of titration videos, so I can't show those on here because that would be copyright to upload them as a video myself, but these links will be available in the hub. So especially if you weren't in class and haven't seen a titration, I highly recommend you watch these. The first one is a little bit shorter, but the second one really goes through in detail of the full setup and all of the equipment used.